Hi, I'm Dr. Scott Simpson, and today we'll be talking about enthalpy and what enthalpy is. So enthalpy is an important state function in thermodynamics. So a state function, again, remember that means it depends only on the initial and the final state. And it's defined as H, so it's given the symbol H for enthalpy, is equal to U plus PV. We've got that pressure volume term that's included, and it's related to the internal energy. That's why this is so important. We're going to find that we have to use enthalpies when we're talking about heat exchanges at the laboratory conditions, most laboratory conditions, constant pressure conditions. The reason we talk about enthalpy, or you've always probably talked about enthalpy in your general chemistry class or other classes, is that's actually related to the internal energy plus this pressure volume term, which we'll talk about in a bit. But it's really related to the internal energy. However, at constant pressure, we don't really have a window to the internal energy, so we use enthalpy to talk about this. So really, what we're trying to do is discuss changes in internal energy, but we have to go through enthalpy. And the kind of neat thing is the heat exchange at constant pressure, that's equal to the change in enthalpy. So, change in enthalpy delta H is equal to the heat exchange at constant pressure. So, pressure. So remember, the heat exchange, that's considered Q, or is given the symbol Q. So let's try to prove this. So we're going to try to prove this. So let's start with the initial definition of enthalpy. H is equal to U plus PV. Then we want to consider an infinitesimal change in these functions. So we're going to take the small infinitesimal change, so we get dH is equal to du. Then, if we're taking, looking at the differential of these two functions together, we're going to have to actually apply the product rule. So remember the product rule, you have d f of g, you get f times dg plus g times df. So in this case, we apply that here, we get p dv plus d dp. Okay, so now it looks like our situation's gotten more complicated, but let's step back for a minute. Let's think of how we've previously described du. So you're looking at the differential of u. From the first law of thermodynamics, we know that u is equal to q plus w, so we get dq plus dw. Now, if we sub this in, it's not going to make our situation any better. What we do have to consider is a system where we only have pressure volume work. So only where PV work is happening. So if PV work, only PV work, then this expression du becomes dq, and that dw changes, it goes to negative p dv. Okay, now we have something that can be used. Let's sub that into this equation, and let's see what we get. So we do that, we get dH is equal to dq minus p dv plus p dv plus v dp. Okay. So now, if you look at that expression, there are some things that can cancel out. These two terms right here, they can cancel out with one another, and we're left over at the expression dH is equal to dq plus v dp. That's what we're left over with. Okay, but we were looking at proving that the heat exchange is equal to the change in enthalpy at constant pressure conditions. So looking at this expression, if we have a constant pressure condition, so at constant pressure, that differential, that dP, that's equal to 0. So this term is going to drop away. What we're left over with is the H dQ, and since we're at constant pressure, we're going to put a little sub P on that Q that indicates that it's at constant pressure. Now, if we integrate both sides of this expression, we said that H is a state function, so we're going to get a delta H on this side. Q is a path-dependent function, so if you integrate infinitesimal change in the path-dependent function, you just end up with that total number there. So we're going to get Q sub P. So we've effectively shown that the delta H is equal to the heat exchange under constant pressure conditions for systems that have only pressure volume work. Okay. So the importance of that enthalpy ends up being a very important state function because that's what we tend to measure most of the time. And there is a relationship there that we previously discussed with changes in internal energy. So with that, I'd like to thank you for watching. If you have any questions or comments, please leave them below. Thank you.